when we look at reactions, we have always written them as going forward. So C6H12O6 plus O2 gives you CO2 and H2O with an arrow pointing in one direction. That's cellular respiration. When we look at CO2 plus water plus energy gives us C6H12O6 plus O2, that's photosynthesis, but we still only put a one-directional arrow. Okay? However, most chemical reactions are reversible. They will go forwards and they will come backwards. Excuse me, this is what it looks like. Let's look at NO2 and we get N2O4. My goodness. Okay, both as gases. NO2 can combine with oxygen and give us N2O4. And N2O4 can decompose and give us NO2. Now, if we did a balanced reaction, we would put a 2 there. So in the forward reaction, right, because the arrow is indicating that we're going this way, in the forward reaction, NO2 is what we would call the reactant, and N2O4 would be what we call the product. In the reverse reaction, which is going backwards, N2O4 would be the reactant and NO2 would be the product. Okay? Because this is a two-directional reaction, this is a reversible, what we call a reversible reaction. NO2 produces N2O4, N2O4 decomposes and gives us NO2. This reaction, as long as there's NO2 in the system and N2O4 in the system, this reaction will always happen because one is producing and one is reacting. Okay? Another reversible reaction is salt and water. We've looked at this lots. We've put table salt in water, and when we put it into water, what happens to the ions? They dissociate into what? Na plus and Cl negative. So sodium will break down, salt will dissolve or dissociate into water and give us sodium ions, potassium ions. And we know that because we can put a voltmeter in there and we can see that electricity is being generated. Or we can see salt start to form out. The sodium ion and the chloride ion will join together and produce salt. Any salt, potassium chloride, potassium nitrate, lithium hydroxide, they're all salts. Okay? If more solid salt is added, eventually no more salt can be added, and the excess salt sits at the bottom of the beaker. Without looking at your notes, this would tell you that the solution is saturated. If we added heat to the solution and that solid went into solution, we would call it supersaturated. Look at you guys go. Okay? Just because when we add salt into the beaker and it is no longer dissolving and is sitting at the bottom of the beaker, even though it's saturated, the reaction is still happening. Salt is still breaking down into sodium ions and chloride ions, and sodium ions and chloride ions are forming salt the whole time. The reaction isn't stopping. When we're at saturation, the big word that we learned way back in grade 8, it's in equilibrium. It's balanced. Okay? They're happening at the same rate. Equilibrium is happening at the same rate. Solid is breaking down and ions are forming solids. So here's the big takeaway. Equilibrium is the rate of the forward reaction equaling the rate of the reverse reaction. That's like your teeter-totter. You're neither up nor down. You're horizontal perfectly. That's equilibrium. In our body, we call it what? Starts with homeo and ends with stasis. Homeostasis, our system is in balance. Okay? It does not mean that there's one sodium ion for every chloride ion. Okay? The reactants, or one sodium ion and chloride ion gives us one salt. It doesn't matter. The reactants or the products, it's happening at a molecular level. When we look at it, can we see the salt breaking apart? We can't see it. It just isn't there anymore. We can't see it. We don't see those bonds breaking apart. We also don't see those bonds forming to give us that crystal. The crystal is there. Remember how hard we worked to make rock candy? Some just sat there forever in solution and some were rock solid the next day. Okay? If it looks like the reaction has stopped, what we can physically see, we call that at a macroscopic level. So microscopic we can't see, macroscopic we can see. Okay? And then, yeah, yeah. And then this piece here is crucial. It has to happen in a closed system, which means that reactants aren't being added and products aren't being taken out. Okay? And it has to happen at a constant temperature. We're going to learn when we get to lesson 3, Le Chatelier's principles. Heat changes things. Why does it have to be in a closed system? So we don't have evaporation or condensation back into the system adding to it, right? Okay. Examples: in a sealed aquarium, liquid water and vapor are at equilibrium as long as the temperature doesn't change. A carbonated soft drink is a closed system where carbon dioxide gas and dissolved carbon dioxide are in equilibrium. The equilibrium is distributed when the bottle is opened and a new equilibrium is established. So right now, I don't know who's left this can of club soda here. No, it wasn't for a while. But we'll use it today. It doesn't matter what I'm doing here. The inside of the can isn't changing. The dissolved CO2 and the undissolved CO2 is the same. How come it fizzes when you shake it sometimes? Inside of here? Okay. Nothing's changed in here, right? When I go to open it, oh, that was snot. It's better with pencil. But you can hear it, right? You can hear it. Okay? What we've done is now we've shifted equilibrium and the CO2 is being released. That's what we can hear. We can hear the bubbles popping of the CO2 inside of the club soda. So now our Lesson 3, principles have shifted. So why, when you have pour it into a glass, say it again, Eric?
Well, since then, but when you pour it into a glass, business.
Yeah, okay, so what was it before I popped the top? Was it an open or a closed system? It was a closed system, nothing could change, right? When you have an open cup and you pour it in, what's happening is that as the water or the pop or whatever it is hits the side of the glass, it makes contact and those bubbles pop and that CO2 is released. And it's shifting the equilibrium balance. And we can't capture that CO2 because it's an open system.
When you're like pouring and like lots of bartenders, they pour it on the side of the glass but it like trickles down to like the definitions for it.
So what happens is, and this is my husband does all the time, because he can't do carbon in the home. So I'll take the glass and he'll pour it from very high, and it creates that violent interaction, and it releases those bubbles very quickly. Whereas if you pour beer or drinks, fizzy drinks down the side of the glass, you create less friction between the surface area and it keeps that carbonation. It keeps the CO2 dissolved in solution. But the minute that we make it a violent reaction or we create that friction, then the CO2 is released from and it's no longer dissolved.
Oh, is that why when you like the glass bottle and pump someone else's glass bottle, or
The vibrations go down through the glass bottle, and if you do it just right, you pull the neck off your bottle. I've had more people do that to me in college and lose my drink because my bottle broke. Because of simple harmonic motion. Okay, because a system at equilibrium can have different amounts of reactants and products, a reaction can either favor products or favor the reactants. If I have a lot of product, or if I have a lot of reactants, is the reaction going to flow towards the reactants or away from the reactants? Away, because it wants to be equal. If I have a lot of product, is it going to flow towards the product or is it going to flow towards the reactants? Towards reactants. Okay, reaction between hydrogen gas and iodine came to equilibrium and the concentration of all species were measured. The hydrogen gas and iodine had a concentration of 0.022 moles per liter, and hydrogen iodine had a concentration of 0.156 moles per liter. What would be favored, do you think? Okay, well, let's look. Hydrogen and iodine are reacted, and they produce 2 hydrogen iodides. Okay? Hydrogen gas has iodine has a concentration of 0.022, and hydrogen iodine has a concentration of 0.156 moles per liter. We're pumping in reactants. What do you think is favored? Right. Don't get caught up in concentration. Okay? The product side of the reaction is favored. So it looks like this. Mm-hmm. All right, so this is the quantity and this is the reaction progress. So at the beginning of the reaction, we have lots of hydrogen and we have lots of iodine. Do we have any hydrogen iodide at the beginning of the reaction? No. As we go along and we consume the reactants. Okay, they're going to go down because we're consuming them, and we are producing hydrogen iodide. Okay, and when we look at this piece here, equilibrium, where would we say equilibrium happens in this diagram? When the graph,
This curve and this curve.
you were really close. When they level off, okay? So when we see this leveling off here, when we see this leveling off, that's when we know equilibrium has been reached, observably. No observable changes. 4 years and you still can't read my handwriting.
I just have to.
Maybe you shouldn't have picked on Nolan at lunch and he'd be willing to help you out. Okay. If the product HI was removed as it was formed, would this system reach equilibrium? So as we're reacting it, we're taking that hydrogen iodide out of the system. No. Why, Declan? Well, that was a really good guess. No, I just have a better answer. The system is no longer a closed system because we're removing something, right? Same concept as an open system. We have evaporation. We're losing that water vapor. Okay, let's look at practice problems.